in the last class we were talking of modeling bicubic surface patches, and for that we had derived this expression that P of uv will be given a umb multiplied by m transpose into v transpose, or it can be given a u into a into v transpose, where a is the algebraic matrix and b is the geometric input matrix. The matrix B is given by this set of 16 vectors P00, P01, P10, P11, Pu at 00, Pu at 01 and so on. Okay. And in this matrix, if you look at this first column, we said that these 4 terms together will specify a PC curve which is the V equal to 0 curve. Similarly, these 4 terms will specify the PC curve for V equal to 1. These 4 terms will specify the auxiliary curve for V equal to 0. This is the auxiliary curve, and similarly this is the auxiliary curve for V equal to 1. Okay, and similarly in this these 4 rows will specify another 4 set of PC curves. First 2 will be PC curve, the next 2 will be auxiliary curves. Okay, and this is how we can formulate this 4 by 4 matrix of the input vectors. Okay. Now, then we also mentioned that if these 4 twist vectors are put equal to 0, in that case this is called a Ferguson patch or a F patch. Okay. Now, what we will see is that instead of inputting a surface through these 16 vectors, these 16 vectors are the 4 corner points, tangent vectors at the 4 corner points, okay, and the twist vectors, which let us say if I represent them by 4 curved arrows like this. Okay, so these are the 16 inputs we are giving right now. Okay, but generally it is difficult to give input in the form of twist vectors or in the form of tangents. Instead of that, we sometimes prefer to give input as points. So if you want to give the input as, let us say, 16 points on the surface, then we can give an array of 16 points at specified values of the parameter u and v. Okay, let us say this is at 0 0, maybe this is at 1 by 3 0, this is at 2 by 3 0, this is at 1 0. Similarly, this maybe it is at 0 1 by 3, this is at 0 2 by 3, and this is at 0 1. Okay, and this is at 1 1. The others you can fill up. Okay, if we give the input as these 16 points, and we say that this bicubic surface patch should pass through these 16 points. Okay, in that case, again we can write down. We know the equation of the curve as P is equal to U A into V transpose. At each of these points, we can write down Pij as Ui into A into Vj transpose. That means I am essentially putting U equal to I and V equal to J in this expression. Okay, and this will give me a set of 16 equations. Okay, I can solve those 16 equations simultaneously to get the 16 parameters or 16 variables required for the A vector, for the A matrix. Okay. If you remember, when we carried out the same exercise for PC curves, okay, for PC curves, when we gave the input in the 4-point form, 0, 1 by 3, 2 by 3 and 1. For the PC curve we had mentioned, or rather we had derived that P will be given by U n multiplied by P. Okay, where this matrix P consisted of these 4 points, that is P0, P1 by 3, P2 by 3 and P1. Okay, this was what we refer to as the 4-point form of the PC curve. Okay, similarly, if you are giving the input in this form, we can derive an expression for the 16-point form of the surface. Okay, and for this 16-point form, we can show that P will be given by U n P multiplied by n transpose multiplied by V transpose. Okay, where this matrix n is the same as this matrix n. Okay, and just to recapitulate, this matrix n, we had given it last time also. It is given by these terms. Okay, so if the input is given in a 16-point form like this, that means if these 16 points are given as input at these locations 0, 0, 0, 1 by 3, 0, 2 by 3, 0 and so on. Okay, then for this 16-point form we can get this relationship where n is given by this matrix. Okay, and P consists of the matrix of these 16 points. Okay, this the detailed derivation for this you can look up from the book, but this result is, it can be shown to be this. Okay, and we have already shown that P is equal to U into A into V transpose. So the set of algebraic coefficients will be equal to n into P into n transpose. Okay, just by equating these two right hand sides. Okay, that so A will be n P n transpose. Okay, and we have already shown A to be M B M transpose. Okay, so this is also equal to M B M transpose. Okay, if you compare it with the formulation for the PC curve, the formulation will be very similar. There A was equal to NP and it was equal to M times B. Okay, so we have a similar formulation in this case also. Okay, the other form of the that we can have for the bicubic surface patch is what is referred to as a 4-curve form. Okay, again I just give the outline. Let us say if this is a surface that I want to create, this surface can also be created by inputting four curves in the same direction. Okay, if I consider this, let us say this is my curve 1, this is my curve 2, this is my curve 3 and this is the curve 4. Okay, I can, these 4 curves can be input, let us say for standard values u equal to 0, u equal to 1 by 3, u equal to 2 by 3 and u equal to 1. Okay, so for these 4 standard values, let us say if we input these curves, then again we can derive the expressions for the algebraic matrix. Okay, we can write down the equation for each of these curves. Let us say P of uv is equal to ua v transpose. In that, if we put u equal to 0, we will get P of 0v will be equal to u at u equal to 0 multiplied by A into V transpose. Okay, if this curve is given, similarly if the other 4 curves are given, we will get a set of simultaneous equations and we can get expressions for A using that. Okay, so if we are given 4 curves, then an expression for A can be derived from those 4 curves also. Okay, the only thing one has to be careful about is that normally we would prefer to give these 4 curves in the same direction. Okay, if I give 2 curves in this direction and the other 2 curves in this direction, that might not be correct, because at the common point we might not be specifying independent variables. We will have to be careful about that. Okay, because in the beginning we have seen that if we give this as one curve, this as a second curve, this as a third curve and this as a fourth curve, then we do not get a unique bicubic surface patch. Okay, but that was because the 4 curves were not in the same direction and we had common points that were being given. Okay, but if we give 4 curves in the same direction, then we do not have problem of this type and we can specify a bicubic surface patch and in this manner also. Okay. Any question up to this point? Okay. The next thing let's see is how to formulate composite surfaces. Let's say we are considering 2 surfaces. Okay, let's say this is a surface patch Q and this is a surface patch P. Okay, and let's say this is a 0 0 point for this surface patch, this let's say the 1 0 point, this is the 1 1 point and this is the 0 1 point. Similarly for this surface or the Q surface, let's say this is the 0 0 point, this will be the 0 1 point, 1 1 point and this is the 1 0 point. Okay. Now what we are bothered about is that at this common edge we should have a certain kind of continuity. Okay, we have already mentioned that for specifying any bicubic surface patch we need 16 vectors. Okay, which means that for any surface, for any bicubic surface, we have 16 into 3, that is 48 degrees of freedom. Okay, so if these 2 surfaces or these 2 surface patches were totally independent, we would have had 48 into 2, that is 96 degrees of freedom. Okay, but since we want to have, let's say, C1 continuity at this edge, the 2 surface patches will not have 96 degrees of freedom. The number of degrees of freedom will be much lower. Okay, so let's just see what how we can ensure that there will be a C1 continuity between these 2 surface patches. Okay, let's take the standard geometric form for the input for both of them. Okay, let's say for this surface, if you write down the standard geometric form, we will get B, that is the input, the geometric input matrix, as P00, P01, P10, P11, Okay. This is the input matrix for this P surface. Okay, for this first surface that I have made. Okay, in this surface, this edge is the edge given by the curve u equal to 1. Okay, so the edge given by the curve u equal to 1, that in this is given by this rho. Okay. Similarly, if I want to ensure a C1 continuity, then along this edge, the tangent vector in this direction should be proportional for both the surfaces. Okay, only then we will get C1 continuity. Okay, and the tangent vector in this direction along this curve is given by the auxiliary curve corresponding to this curve, by the u equal to 1 auxiliary curve. Okay, so the u equal to 1 auxiliary curve is given by this rho. Okay, so if we want to ensure C1 continuity between these two, then the u equal to 1 curve for this patch and the u equal to 0 curve for this patch should be identical. Okay, that will ensure a C0 continuity. That means these two edges will be common. Okay. Secondly, the auxiliary curve along this for the Q patch should be the same as the auxiliary curve along this for the P patch. Okay. So now if I want to write the B matrix for the Q patch, okay, let us say that this is B for P and this is B for Q. Again, this is a 4 by 4 matrix, and the first row is the u equal to 0 is the u equal to 0 curve, and the third row will be the u equal to 0 auxiliary curve. Okay, the second row will be v equal to u equal to 1, and the fourth row will be u equal to 1 auxiliary curve. Okay, and now to ensure a C1 continuity, here the u equal to 1 curve for P and the u equal to 0 curve for Q have to be identical. Okay, which means that this first row here has to be the same as this row. Okay, so the first row here will look like P10, P11, PV at 10 and PV at 11. Okay. Similarly, the third row here should be proportional to the fourth row over here. Okay, only then we can ensure that the tangents are in the same direction everywhere. Okay, so if that is to be ensured, this fourth row here will get repeated here in the third row with a constant attached to it. So Pu at 10, Pu at 11, Puv at 10 and Puv at 11. So these four terms will come here with a constant attached. Okay. Only then the tangent vectors along this edge will be in the same direction. The magnitudes can be different. Okay. So for the input matrix for the Q patch, out of the 16 terms, 8 terms will get fixed like this. and the remaining 8 terms can be anything. Whatever the remaining 8 terms be, the 2 patches will always have a C1 continuity at the common edge.
72 degree freedom.
Again?
72 degree of freedom.
72 degrees of freedom. I don't think so. We will just calculate our degrees of freedom. Okay. Let's come to that. The number of degrees of freedom for these 2 surfaces put together. The first surface has 48. Okay. The second surface, we can input 8 vectors, that is 8 into 3 plus this constant. Okay, so 48 plus this will give us 73 degrees of freedom. Okay, because this auxiliary curve and this auxiliary curve, they can be proportional. So we have introduced a constant C, and the magnitude of this constant C can be changed. So that gives us an additional degree of freedom.
When we say C1, we aren't concerned about the magnitude of the vector, we just say the direction.
Yeah. The direction should be same, the magnitude can be different. Okay. So this way, if we are having 2 adjacent composite surfaces, instead of having 96 degrees of freedom, we will get 73 degrees of freedom. Okay. And this concept can be extended further to having an array of composite surface patches. Where each segment that I made here is a surface patch having a C1 continuity along this edge for the next one. Okay, so let's say if I call this as a P11 surface patch, this is a P21 surface patch, and so on. Okay, this is a P12 surface patch, and between these two we will have a C1 continuity over here. Between these two we will have C1 continuity along this edge, and so on. Okay, so a formulation for having a, let's say, n cross m array of composite patches can also be made on similar lines. Okay, in fact you will find such a formulation given in the book. If you want to look at the details, you can look into that. Okay. Any questions regarding bicubic surface patches? Okay. Then let's take up the next type of surfaces. Those are the Bezier surfaces. Okay. We have earlier defined Bezier curves. Again, for Bezier curves we have mentioned P of u will be sigma pi multiplied by bin of u. This was for Bezier's curves. Okay, in this case we are giving a set of control points as the input, and a curve is being defined between within the convex hull of these points. Okay. Now, instead of having a single one-dimensional array of points, we will talk of a two-dimensional array of points. Okay, that means if let's say this is the array of points that is input, I am joining them right now by simple straight lines. Okay, within these we can define a Bezier surface which might look, let's say, something like this. Okay, and let's say it will have a family of Bezier curves in between. Okay, so we can define a Bezier surface in this manner, where let's say in one direction we can have n plus 1 points, in the other direction we can have m plus 1 points. Okay, earlier we were defining our points from P0 to Pn. Okay, now in one direction we can have points going from 0 to n, in the other direction from 0 to m. So this way we will get an array of m plus 1 cross n plus 1 points. Okay, and the mathematical formulation for Bezier surfaces would be okay, where the summation for I will be from 0 to n and j will be from 0 to, let's say, m. Okay. So in the case of this Bezier surfaces, you will find that the degree in one direction can be n, in the other direction it can be m. Okay. So if you are talking of a bicubic Bezier surface, okay, for that we will say n will be equal to m will be equal to 3, and the total number of points will be 4 by 4, which will be 16. Okay, and then for a bicubic Bezier surface, we can say that we can show that P of uv will be equal to, let's say, f of u multiplied by p multiplied by f of v. Okay, if you compare it with what we had for Bezier surfaces, we were saying p was equal to f multiplied by p. P was the array of control points. Okay, in this case we can say f of u multiplied by p multiplied by f of v. Okay, where f of u, that can be, let's say, for if you are talking of a bicubic surface patch, we can say that this will be okay, and similarly f of v will be having similar terms containing v. Okay, so this will be the transpose of this, and the f of v will contain terms like okay, and this what I have written is only for the case of n is equal to m is equal to 3. Okay. For a bicubic Bezier surface, if we have a surface which is given like this, this surface has to pass through the 4 corner points. Okay, because let us say this is my point which is the point 0 0 in the array. Let us say this is the point which is n0, this is the point which is nm, and this is the point which is, let us say, 0m. Okay, this is the corner point I have taken over here. Okay, this surface will pass through these 4 corner points. Okay, but it will not pass through any of the other control points, just like we had in the case of Bezier curves. Okay, because this surface is a approximating surface and not an interpolating surface. Okay, these 4 bounding curves that I have drawn right now, this curve, this curve and this curve, these 4 bounding curves, they will be Bezier curves. Okay, this can be seen easily from this formulation. Okay, Pij into Bin Bim. If I put Ju equal to 0, okay, I will still get the form of a Bezier curve. Okay, similarly, if I put Ju equal to 1, I will still get a form of the Bezier curve, and so on. Okay, so this in this surface, these 4 bounding curves, they will be Bezier curves. So what that means is, if I consider this curve is defined using these 4 points. Okay, so if I draw the view here, that means that on this curve the tangent in this direction will be from here to here in this direction. Okay, that means this will be the direction of the tangent vector, because this is a Bezier curve. Okay, so direction of tangent vector has to be from one first control point to the second control point. Okay, similarly, the tangent vector at the end will be in this direction. Okay, and the same thing can be said about the other 3 surfaces or 3 curves also. Okay, that means for a bicubic Bezier surface, when n is equal to m is equal to 3, the points P00, P03, P30 and P33, these points will define the 4 corner points. Okay, but if I consider the points P01 and P10, they will control the 2 tangent vectors at the corner, at the point 00. Okay, this point is P00, and this point that I had made, this is the point P01, or sorry, P10. This is the point which is P20, and this is the point which is P30. So 10 and 00 will define the tangent vector here. Okay, so in addition to these points, P01 and P10 will be controlling the tangent vectors at this corner point. Okay, similarly, if I consider this point, we will get P20 and P31. These 2 will control the tangent vectors at this point. These 2 in conjunction with point 30. Okay, so if I consider, I will just draw a rectangular array. Okay, these 4 points control the 4 corner points. Okay. These two will control the tangent vector in these two directions. Okay. These two will control the tangent vectors in these two directions. Okay. These two will control the tangent vectors in these directions. These two will control the tangent vectors in these directions. Okay, so out of these 16 points, 4 are controlling the corner points and 8 are controlling the tangent vectors. Okay, and these 4 okay, they will be controlling twist vectors at the 4 points. Okay, so if I specify these 12, I can specify the 4 bounding Bezier curves. Okay, but these 4 will help us control the twist at the corner points. Okay, the twist vectors or the cross slopes or twist vectors. Okay, and again we can say something we said earlier for Bezier curves, that if I are given this array of input points and I change any of these points, my tangent vectors at this point will not get affected. So at this point the tangent vector in this direction will be controlled only by these 2 points, and the tangent vector in this direction will be controlled only by these 2 points. Okay. Similarly, at this point the tangent vectors are controlled only by 3 points, and we can extend that to a general surface of degree n. If we have a surface of degree n, if I consider k points in this direction, the kth derivative will be controlled by only those k points. Similarly, k points in this direction will control the kth derivative in that direction, and so on. Okay, that is a property which is specific of Bezier curves and Bezier surfaces. Okay. So we can define bicubic or we can define Bezier surfaces using this kind of formulation. Okay. Any question with respect to the Bezier surfaces?
16 is the minimum number of points we have to give. We can give more points of form than controlling it.
16 is the number of points one has to give for a bicubic Bezier surface. Okay, that is when the degree in both directions is equal to 3. Okay, if you have a higher degree curve, we can have higher number of points. Okay, if you want to have a quadratic Bezier surface, then you need to give only 3 into 3, 9 points. Okay, but normally cubic is the lowest degree one goes down to. Okay. Anything else with respect to Bezier surfaces? Okay, similarly, if I have a higher degree Bezier surface, that means I have n plus 1 cross n plus 1 points. If I change any of these intermediate points, my continuity of the corners will never get affected. A continuity will be affected only by k points in this direction, k points in this direction. So if I want C1 continuity, only 1 point here and 1 point here, that will only affect my continuity. Okay, so if n and m is large, that can be important in controlling the continuity in the case of composite surfaces. Okay. Anything you want to know about Bezier surfaces? Okay, in that case let us quickly see how we can define B-spline surfaces in a similar manner. Okay. So if you want to define B-spline surfaces, we will extend the definition of B-spline curves and we will say P of uv will be given by summation in both the direction Pij Nik of u multiplied by Njl of v, okay, where I goes from 0 to n and j goes from 0 to m. Okay, just as we have defined B-spline curves, now if let us say this is a general surface that we want to define, we have number of points in this direction going from 0 to n, the number of points in this direction going from 0 to m, and in addition to that we define the degree of this curve in this direction as k and the degree in this direction as L. Okay, so this K and this L will control the degree of local control in the two directions. Okay, and the definition of Nik and Njl will be done in a manner similar to what we had done for B-spline curves. Okay, these definitions will remain the same. Okay, so if you are defining a bicubic B-spline surface, we will put K equal to L equal to 4, that will define a bicubic B-spline surface, and the number of points in either direction can be anything. Okay, so we will be able to define an array of surface segments or surface patches as we are defining curve segments for B-spline curves. Okay, and all the properties that we had for B-spline curves will also be extended to B-spline surfaces. That means a degree of local control will be there, and in addition to that we can define closed surfaces, we can define what we had periodic and non-periodic surfaces. Okay, if you remember we had defined periodic curves, and for closed periodic curves, if we had an array of points like this, a closed curve or a smooth curve like this. Okay, similarly we can define periodic surfaces, and we can define closed periodic surfaces which can be totally closed surfaces. Okay, for example, we can also have surfaces like this. Okay, this is closed in one direction, open in the other direction. Okay, periodic in one direction and non-periodic in the other direction, and so on. Okay, so the basic definition of the B-spline surfaces will be given by this, and on top of this basic definition we can define periodicity and we can define closed and open surfaces in either direction. Okay, in one direction it can be open, the other direction it can be closed, in one direction it can be periodic, in the other direction it can be non-periodic. Okay, so we won't go into details of these surfaces. The basic idea behind these surfaces is that these surfaces are essentially giving us an array of surface patches. We get an array of surface patches like this, and each patch will have a degree depending on the degree of the B-spline surface. So let us say if you are taking a degree K here and a degree L in this direction, then each of these patches will have a degree K and degree L, and the number of points controlling each patch will be governed by these parameters K and L, while the total number of parameters might remain anything. Okay, so this is how we can define B-spline surfaces. Okay, any questions on B-spline surfaces? Okay, so with that I will close this topic of surface modeling. From the next class we will see how we can model solids and how we can represent solids for different applications.